So yeah, quality service is about or includes some kind of prioritization. The idea is shown here in this image. If you think of this pipe, and that's just for illustration purposes, but this could be a fiber, or it could be a Wi-Fi connection, some kind of connection which is giving some kind of service over a network. So it's really in the context of a network. If we think of that coming to us, we could that service, that network service, could be providing all kinds of benefits to our customers. And so we could be carrying voice, we could be carrying certain types of applications, many applications that our business has. We could be carrying video. And we could be doing some best efforts for extra things that are happening on the network. And the idea of quality of service is that certain of these services would be prioritized above others. And so if the situation came that the demand was greater than the supply, or the supply of network service that was able to be given by the system didn't meet the demand, then we have some logical formal way of setting the network so that the highest priority applications, the highest priority users, if you want to look at it that way, are receiving a prioritization on getting that service. So different users, different applications, different data flows could be given different amount of that service. So as you saw in the previous image, we imagine dividing up the network sort of capacity, and then rationing it out based on some sort of model that we've come up with, and here it's referred to as class-based weighted fair queuing. So you could have, and this diagram shows this too, I think, quite nicely. You could have a situation where you have two applications accessing the router at the same time, and you have one application which is low priority. Now you might look at that and say, oh, well, computer users should be as high a priority as phone users. Well, maybe this computer user is playing video games, or watching YouTubes or something, right? So that's been set as a low priority in our business. And so even though these two services are trying to access the router at sending the same sort of requests or the same data through to the router, only the higher priority service is actually getting through the router, and the other one is not. So you may have seen that here at the college. It used to be that I know that they used to be applying a quality of service which would limit your videos. I'm not sure if they're still doing that, uh, but they used to do that, and I guess the reason for that was would be obvious, right? I mean, we need to use the networks in the college for our business um, applications of student access to PeopleSoft, stuff like that. Um, Now, I'm saying maybe because I know the network's being upgraded all the time, and and the other that's one reason to not have to sort of ration video. Another reason not to is because now that's become part of our core operations, right? Video, because we're all using Zoom. Here we are, right? Video. But but we could prioritize Zoom over WhatsApp video. We could prioritize Zoom over Skype video or something like that. So you do see that happening. Now, it can happen at the organizational level, like here at the college, or it can happen at the service provider level, like Aredo. And so I have noticed that depending on how whether you're using a VPN or not, can also make a lot of difference on that. It used to be that certain video applications would be hard to sort of get through the the Aredo firewall. Um, so why is quality of service important? Well, because there is a limit to our capacity on our networks, and we want to make sure that that capacity is utilized for the applications which have the highest priority. So I hope that makes sense. And so if you had to choose between these things happening at your work, do you want people sitting there watching Netflix, at work? So well, could be no, you don't. So what you'll do is you will uh, put the priority of Netflix very much lower. Now, bearing in mind with the digital networks that we have nowadays, which we've had for 30 years or whatever, um, the data is traveling in packets. And so if you're going to put some kind of priority on a particular type of packet, then you have to have some kind of software which is able to identify the different types of packets. And yeah, I mean, it's an arms race. And what I mean by an arms race is that different uh, different types of services, different packets. They work to avoid detection by the various firewalls, and the on the other side of it, the people who are trying to implement a quality of service with their firewalls um, are always coming up with new ways to identify particular types of packets. So you may offer in your SLA, I hope you all remember what an SLA is, your service level agreement. So the important words in the service level agreement in the SLA, service level is very important. It's not just a service agreement, it's a service level agreement. So in the service level agreement, you guarantee or a certain level of service to your customer on a certain application. So you may have so we're talking about the IT support group here usually. This might be internal or it could be IT, well, Arito, anybody who's offering a communication service would have some kind of service level agreement with their customers. Now, you might say, well, I have a phone. I don't remember signing a service level agreement with Arito. Well, in fact, you did when you signed up for your applications, your Rito applications, you did have to sign a contract, and you will have a different contract depending on on how much you pay monthly and what services you get. I mean, so some people get a higher level of data, and yeah, so I mean, we have a service level agreement with them, and just like we have that service level agreement with Arito, we have a service level agreement with internal customers in an organization like the College of North Atlantic. We have an IT department downstairs. The IT department downstairs provides a service to the general sort of students and staff, which are represented by their departments, and then by the senior management of the college. So the senior management, depending on how they look at that, they will make some kind of service level agreement with the IT department, and they provide a certain amount of money. The IT department uses that money to produce to buy the equipment that they need, and then provide a certain level of service. All right, and that certain level of service will have some things that we will use to measure. How are we giving the service that our customer needs? And well, a customer might just look at it simply from the outputs of that, which is, how long does it take me to download videos and stuff like that. But there's some other more sort of precise measurements that we can have, I suppose. And here's some of those things there where we can measure this thing called jitter. And jitter is a negative sort of idea. The idea of jitter is that if we're sending a stream of packets, the packets are getting through, but there is some disruption in the timing. So then they're not coming across in a steady stream. So that even though we got our 5 packets through, the 5 packets that we sent, we got our 5 packets through, there was a bit of a congestion in the network. And so when we measured our jitter tells us that there's some congestion in the network, and that is going to lead to some longer sorry, that it's going to reduce our throughput. And you'll see the last slide in this deck of slides, it talks about throughput. And throughput is basically, that's the end goal that we want to get to, is how much can we get through for our customers in the least amount of time. Oh, there we go. And here we have a slide where we're measuring various things that impact upon the throughput. So throughput, we got a definition of it a bit later on, but it's not just the number of packets that are getting through, but it's the actual packets that successful, that successfully go from one end of the network to from the source to the destination. So we can just throw a lot of packets onto the network, but if they're not, and they may go through a few nodes in the network, but if they're not getting through to their destination, they're not measured as a positive in the throughput, right? So they're measured as a negative. And so these things here, so data jitter I just mentioned, but also data loss, latency. Latency is actually sort of directly related to throughput, because latency is, the time that we wait between when we put the thing on the network and when it's received. But these other things, data loss, you could be sending a lot of data along, and if we're losing it, it's going to have to probably be resent, right? And so your throughput is going to be measured only on the positive ones. So this is going to reduce your throughput quite a lot as well. And data jitter we spoke about. So throughput is only going to be the successful delivery of packets that are put onto the network. And so we measure throughput for the system, or aggregate, which is aggregate means the total. The system is going to be for the entire system. So it's going to be the total amount of data packets that have got through compared to what we tried to get through. And so we've got some little mathematical symbols that you might sort of recognize there, lambda and mu. So they're going to be put into some equations that we're going to use to calculate mathematically using this special mathematical theories called queuing theories. We're going to be able to measure our throughput from that. And so it's going to be the load of packets per time, and that's lambda, and the throughputs of packets per time as mu. Okay, so here we have a diagram which is sort of representing this, and some notes there that will help us to understand how latency is affected by different technologies. So our latency, first I guess we need to define that. So latency is going to be a time that we wait. Time that we wait for what? A time that we wait for everything. It's right. It's like end-to-end waiting. So it's going to include queuing time, processing time, and our transmission time. So we're adding all those things into a time, which we then call latency. Latency is going to be measured in, well, seconds or milliseconds, some part of seconds. Now, why did I say seconds? Depending on the medium that you're using. I mean, are you using wire, or are you using fiber, or are you using satellite? The latency will be different depending on those. And as we see, satellite takes a little longer. You can tell that if you made a phone call, which is an international call, you can tell if that call was going through a satellite, because you sort of hear echo there, or you say something and then you wait a second before you hear them talk back. Now, it might not be too obvious why that would take longer, but I think it just has to do with the actual great distances. So even though you're going around the world, so let's say we're making a phone call from here to maybe India or something like that, and we're making that phone call through a satellite. So what's going to happen is that there's a lot of fiber in Qatar. And so, yeah, the first part of that journey of that phone message is going to be through the fiber here, then to a satellite transmission. I think I've seen these transmission satellite dishes. There's on the road, if you go between between Shahanaya and and not Zakrit, Zubara. There's a road that goes up there between Shahania and Zubara, and on that road there's big satellite dish. I don't know if that's the one, because there's also another one down there on Salwa Road. So, anyways, there are satellites in Qatar, and they're able to, satellite dishes, which are able to communicate up to the satellite. Now, the satellite's not really that far away. It's 1,000 kilometers or something less than that, maybe 500 kilometers up. And so, anyways, apparently it takes time, but that's what we have noticed. Fiber's much less now. As I said, it's not intuitively obvious to me why the satellite takes time, because that message is radio waves travel at the speed of light, and fiber optics travels at the speed of light. But so I think it must just be the distances, or maybe there's some sort of transmission sort of process that happens in the satellite. So as well as sort of waiting because of that latency that we were referring to there, there can be some actual loss of packets as it goes through the network. This diagram is just to show that sort of happening, that loss can occur on the network. The idea of this diagram is various vendors, providers have various products that they use to sort of identify that loss and overcome it. So packet loss is a bad thing. Packets can be lost for a number of reasons. As it says, the signal could be degraded. Well, we call that degradation. We call it attenuation. I'm sure that you've heard of it, but the signals that you send on a wire, over a fiber, or to a satellite, over a certain distance, and that distance varies with the technology, but over distance, the signal actually fades a bit. And the problem is that there's, when you send a message, there's the signal itself, and there's also some noise. And the noise is going to be picked up by the receiving device, as is the signal. And as the distance between the sender device and the receiving device increases, then the signal reduces in strength, but the noise doesn't. And so you get to a point where the noise and the signal sort of go into each other, and then that means that the signal is basically lost. So that's one reason it could be lost. If the channel is too congested, if the medium is too congested, packets could just be dropped out. They can't get through. They could be rejected at different nodes in the network. Different nodes in the network could be faulty, not working. Some of our protocols that we use, they could cause some problem there. So we got our dynamic source routing. So routing protocols, they could be causing some problem with the packets. All right, so there, and of course we could have attacks on our networks. Now, we often refer to network capacity in terms of sort of pipes, and the reason why we use the pipe analogy is because different pipes, it's easy for us to understand sort of water flowing through a pipe. If we have a fat pipe or a thin pipe, we know that if we have a fat pipe, we're going to get a lot of water going through there faster. Well, assuming that they have the same pressure behind them. But a fat pipe with the same pressure as a skinny pipe, a lot of more water is going to come through it faster. And that's the idea that we have now. We're not passing water, we're passing packets. So how is it that we get a fat pipe when we're talking about packets? Well, we refer to that as bandwidth, right? So bandwidth is basically a measure of how many packets per second, or the term there is bits per second. And so our bits per second, they're so big nowadays that we're sort of measuring them in giga, which is billions, isn't it? So we have kilo, which is thousands, mega, which is millions, and we have giga, which is billions. So billions of bits per second. Now, bearing in mind that a single character from a keyboard on your computer is not going to be a bit, it's going to be a byte, which is going to be, your 8 bits at least. Depending on the different bytes could be different sizes, but your smallest one's going to be 8 bits. So your bits per second, that's not the characters per second. You're going to need at least, you're going to have to divide that by 8 at least to sort of get a measure of what is going through there. Now, an actual packet, depending on the protocol that you're using to send the packet, it's going to contain kilobytes of data in the packet, and those kilobytes will include headers, and so there's a lot of space there that's not actually pure data, but you need to have the headers on the packets, otherwise the packets don't sort of get reassembled into a proper signal at the other end. I mean, what I'm telling you, all of this is stuff that you all know because you've done all the networking courses. But I'm hoping it helps you to sort of put this together. So the thin pipe, the problem is your latency is going to be longer, but also your download time is going to be longer. And so the general time that it's going to take to get your data from, for example, the server to your client, or the other way around, is going to be a lot longer. The latency is about the same for the fat pipe, it seems, but the download time is going to be a lot bigger. And so that means that your time is going to take longer to get that data. Hope that makes sense. Right, so here we have a shopping list of different techniques that are used by people working in the IT industry, in the networking industry, to overcome some of those problems that we've talked about there. So how do we get the most throughput? How do we get the most data from one sort of point to another over the network? What kind of things can we do? And this is an area of great research. So this does change from time to time. It's updated. New protocols are being brought out. And as the new protocols are brought out, the same media can carry data at a higher rate. And so, but these are certain things that are done to sort of make that happen. Okay, so first one mentioned here is deduplication. The idea being when you send a whole lot of data from one point to another, a lot of that data looks the same as other bits of data that are in that data stream. And so the idea of deduplication is that we can just send the one type of data sort of once, and then any duplicated ones of it can sort of just be indexed to it. And so that we end up sending a lot less data and still getting the same information from it. So that's deduplication. I guess you could think of it as kind of like, well, I'm going to send a lot of the word the. Well, every time I send the word the, instead of sending the word the, I'm going to replace it with an index to the. So the will come through, but only once. So then there's compression. We can do some sort of fudging on compression. Compression is going to take out a lot of those sort of space things that fill up files. And we have different compression protocols that you may have come across, ZIP and RAR and ARJ, etc. ZIP is sort of built into our Microsoft products. RAR is, a lot of people have been uploading RAR things also. So that takes a lot of the space. We got 10 minutes left, but that takes a lot of the space that's sort of filled up in a file. Takes that out and sort of makes it smaller. Now, the idea here is that actually sort of takes some time. There's some overhead that's required to do a compression and then do a decompression. And but we will notice that if we can compress the headers, that we can get a larger throughput as opposed to a header which has not been compressed, where we get the throughput is less, and so our delay is more. So compressing is going to get more data through further. And the compression techniques that we use are like these. Okay, so I don't know if you remember from back in your previous courses that you've done, different protocols at different layers in the protocol stack, but you might remember TCP and UDP. So TCP is going to it's going to control the packets. It's not just going to sort of drop them out there. It's going to control them as they go. And so with that, we have a bit more sort of security, and we have less sort of drop packets. Because it's requiring acknowledgements. It's a congestion control algorithm. And yeah, so TCP helps to reduce some of the problems that we're talking about with sort of congestion and with packets being dropped and that types of thing. And you would remember that perhaps from your previous classes that certain types of applications lend themselves to TCP and others lend themselves to UDP. If you really need to make sure that you're not dropping any packets, then you're definitely going to be using TCP. If you don't care and you just want to send the stuff as fast as you can, and you don't care if you lose a lot of the data, then you're going to use a UDP. And so that's why if you're sort of streaming video, you might use a UDP. But if you're doing a banking transaction, you definitely use TCP. Caching. The idea here is that there's certain stuff that we keep accessing on servers that might be remote from us through our network and maybe even through the internet. These bits of information, we use them over and over again. And so we can cut out some of that access on the network by just, if we know that this stuff is being used over and over again, like I'm always going and visiting Amazon or whatever, then we can put a copy of the last time that we saw what was there the last time. We can put that onto a server, which we're going to call a proxy cache server. And when we go to try and access that that server, the remote one on the network, instead we access the cache server and we visit what's there. Now that is good and it's bad. It's bad if you're doing if you're working on updating data on a remote server and you have and you're working on it on your laptop or something like that, you're refreshing it through FileZilla. You might refresh it and then you go to check the work that you've done on the remote server and it's like, oh, nothing happened, nothing changed. And that's because you're not actually seeing the stuff on the remote server. What you're seeing is what's been cached. And so which case you need to refresh the cache. Anyways, but I hope you understand the reason why the cache is there, right? It's there so that you can reduce your network load, which is the same with many of these things. And same with this sort of forward error correction. What we're doing there is we're inserting an extra packet at a regular time through the packet stream, and that packet allows you to sort of reconstruct the data in case any is dropped. So this reduces the amount of retransmission, and that's sort of shown in this diagram. If you have your forward error control, you're having to do a lot less sort of retransmission data. Protocol spoofing. Chatty applications, what you can do is you can bundle them sort of together. So therefore you can reduce the amount of traffic on your network. So I hope you see a lot of the stuff that we're talking about here. Quality of service is the topic of this lesson, and the key thing that we're trying to do is we're trying to make sure that the very high priority applications are getting their data. Sometimes that might be that we have to reduce the data that's being passed to other applications, or even cut them off. But other times it might be that we're just using little tricks to sort of increase the sort of throughput that we actually get. Now, traffic shaping, that's going back to what I just said about sort of cutting certain things off. What we know is that we have certain applications that we really care about, and we want to make sure that those applications get through. And you can see that in this sorry, it is a diagram. Sorry, my mouse is not being controlled by me very well. You can see this in this diagram. That shows it pretty well, I think. Our business critical applications and our email, we put a big priority on them, but we see that without shaping, recreational, and that's sort of people playing computer games or whatever. Oh, I'm lagging. Yeah, I know you've all heard that, right? So that's because of so that's something that is a high demand on the network for sure. If you've ever been lagging, that means that you have a high demand on the network. So if a lot of people playing computer games on your computer system at work, well, that could be crunching down your business critical applications. And so as a management in the company, you could put this into the service level agreement that there's a certain amount of the bandwidth that we absolutely reserve for business critical applications, and a certain amount that we absolutely reserve for email, FTP, etc. And recreational, we're not going to stop it, but we're going to make it kind of small. So recreation will never be able to take up any more than this small amount of bandwidth on there. And so how that will be observed by our people working in the organization is that sometimes when they try and use recreational aspects, recreational sites or whatever on the network, they might find that that goes kind of slowly. But the good thing is that when they want to use their email or the business critical applications, that they'll be working at a satisfactory rate. And that's because we've implemented traffic shaping, which is part of, this is kind of like the poster child for quality of service. Equalizing, now that's a totally different thing, but basically that's using some very fancy statistics that are sort of applied in an application on your network nodes that are able to sort of analyze the data patterns over time, and that software is able to use the statistics to do something like, well, okay, so in the past it's been like this. We have this spike, then we have this dip, we have this spike, and then we have this dip. So what the software is going to do is it's going to take that spike and cut it off, and then put the dip, take the spike and drop it into the dip. So what that means is we will have a maximum traffic flow of a certain amount, but we'll still get all of our data through with the same, the time hasn't increased for getting all of that data through, and we haven't had to increase our pipe width to do that. We've been able to do that with the pipe width that we had. So I mean, we are able to get a high speed with the limited data pipe that we have, or so that's the idea of that. Another thing you can do is you can sort of certain departments or certain users, certain applications, you can just sort of set them so that they have a very small part of the pipe. And so that's what's happening here. You got server that allows you to control the actual access that they have in terms of the space. You can put rate limits on, and we'd see that the when we use shaping with a buffer control, we can reduce the size of buffers that are required, and so we got that limit, and therefore we're going to get more data through in a certain time. I don't know if you guys have used Wireshark. I don't know. Are you using Wireshark? So something like that. If you have used that,
Yes, sir, we did.